Section 5.5, Zeros of Polynomial Functions. Something I should say about polynomial functions and their zeros. This is something that has been of interest to people for a long time, and so much so that some of the things that happen with the zeros of polynomial functions have almost been looked at ad nauseum. And if you're not quite sure what that means, you can look it up. Just Google it and see once what shows up. But the zeros of polynomial functions, we'll be looking at a lot of different theorems. Once you get the gist of the theorems, then they're really not so bad. So the first one, division algorithm for polynomials, it says if f of x and g of x denote polynomial functions, and if g of x is a polynomial whose degree is greater than 0, i.e. we have a polynomial here that has x's in it, then there are unique polynomials q and r such that so f of x divided by g of x is equal to q of x plus r of x over g of x, or f of x is equal to q of x times g of x plus this. Basically what this is saying is if we have a polynomial, we can break it up into two polynomials multiplied together plus some sort of a remainder, some sort of leftover number or polynomial. So r of x can either be the zero polynomial or degree. This here has to be a degree less than this. So basically what this is saying is given a polynomial, we can always break it up with some sort of a remainder. Then if f is a polynomial function, this is a remainder theorem. If f of x is divided by x minus c, then the remainder is f of c. Now this is kind of very helpful actually, because we're saying if we have a function and it's being divided by this, meaning if we take a function and we try to break it up, we try to factor it into something like this, the leftover part, well then whatever that remainder is, whatever this part right here is just f of c. So I can find this part by putting in the value of c, this number right here, into the function. And what that will tell us very quickly is if we have a zero or not, so if we can or cannot factor it. So that's what this remainder theorem is saying. Trying to practice with it. Find the remainder when this function here is divided by this. Well, when this function is divided by this, we're going to get a remainder that would be the remainder that we're going to get a remainder, the same remainder that we would get when we put 4, whatever makes this 0, into the function. So if we put 4 into the function, we would have 4 to the third minus 2 times 4 squared plus 1, which is 4 to the third, 16 times 4 is 64, minus 4 squared, 16 times 2, 32, plus 1. 64 minus 32 is 32, plus 1, 33. So our answer here would be 33. The remainder, so if we take this function, this set of directions, divide by the x minus 4, we are going to get a remainder of 33. And the way I found that remainder was by putting this, what would make this 0, into the function. So 4 minus 4 would be 0. The 4, or this without the sign here, is what's the remainder. Again, in this case, find the remainder when it's divided by x minus 5. This is just to show you how it works with a little bit different sign. When the remainder is divided by x minus 5, we are going to get a remainder that would be the same remainder as if we put negative 5 into the function. So it's what makes this divisor 0. And if we put negative 5 into this function, we would get negative 5 to the third minus 2 times negative 5 squared plus 1, or negative 125 minus 2 times 25 plus 1, which is negative 125 minus 50 plus 1, or negative 175 plus 1, which is negative 174. So using this remainder theorem, when it's divided by this, the remainder is f of c. I just take what would make this 0, put it into the function, and that is how we get our remainder. What's cool about this with the factor theorem, so if f is a polynomial function, then this factor, the factors we've been looking at, is a factor. So this is a factor if and only if f of c is equal to 0. So if we take c and we put it into the function and get 0, then we can be confident that this right here is a factor. And what that does, it helps us actually factor these things. So it really consists of two separate statements. We have, if we know that a number gives us a 0, then the x minus that number is a factor. Or alternately, if we know x minus a number is a factor, then we know that f of that number is 0. Those two things. So using this factor theorem to determine whether the function f of x equals 3x to the fourth minus 2x to the third plus x plus 1 has the factor fx plus 2. Well, I'm going to use the second part right here. So this part right there, I'm going to use that to determine if this has the factor x plus 2. So if this is a factor, let's see here. So if it's a factor, then when we put c in, or that number, so the number is what makes this part 0. If I put negative 2 in, because that makes that 0, and it's equal to 0, then it's a factor. So if I actually do that, 3 times negative 2 to the fourth minus 2 times negative 2 to the third plus a negative 2 plus 1. This would be 3 times 2, 4, 8, 16. 3 times 16 is 48. This is negative 2 times negative 2 times negative 2 times negative 2, which is 2, 4, 8, 16. So we get plus 16 minus 2 plus 1. 48 plus 16 should be 64. 64 minus 2 is 62, plus 1 is 63. So when we put negative 2 in, we get out a value of 63. When we put in negative 2, we get out a value of 63, which means we did not get 0, so the x plus 2 is not a factor. Another theorem is the number of real zeros theorem. A polynomial function cannot have more real zeros than its degree. So when I look at this function down here, I look for the degree. I look at the largest exponent. The largest exponent is 4, which means this function has degree of 4. The maximum number of real zeros this function can have is going to be the degree. So the answer to this question, what is the maximum number of real zeros this function can have, is 4. Now the number of real zeros might be less than that, but we know for sure that the maximum it can have is 4. And then we get another theorem. It's Descartes' rule of signs theorem. What this says is let f be a polynomial function written in standard form. So if we put the polynomial into standard form, that's where the exponents on the variables are descending, then the number of positive real zeros of f either equals the number of variations in the sign, how many times the sign is changing, or that number less even integers. The number of negative real zeros is either equal to the number of variations in f of negative x, or that number less than even integer. Well, what in the world are all those things actually saying here? If we take a look at this function, f of x is equal to 5x to the fourth minus 2x to the third plus 7x squared minus x plus 8. That's written in standard form. It's descending. The powers are descending down. The maximum number of real zeros is the same as that exponent. So this has degree 4. The maximum number of real zeros is going to be 4. It's the same as the degree. Here, the number of variations in the sign of the non-zero coefficients. So when it's looking for the number of variations, non-zero coefficients, this is positive, positive to negative, that's 1, negative to positive, that's 2, positive to negative, that's 3, negative to positive, that's 4. The number of variations in signs of f of x is 4, which for this rule of signs expectations, if we know that in f of x we have 4 variations, the number of variations, then the number of positive real zeros, what we can expect, positive real zeros, so positive numbers that would make this 0, is going to be either 4 or less an even integer. Well, 4 less 2 is 2. That's a possibility. Or less 2 is 0. For the number of positive real zeros, it's either going to be 4 of them, 2 of them, or none of them. The next thing we got to look at for this Descartes' rule of signs expectation is f of negative x. So if we find f of negative x, we would have 5 times negative x to the fourth minus 2 times negative x to the third plus 7 times negative x squared minus a negative x plus 8. This here, a negative raised to the fourth power, is going to be positive, so it's 5x to the fourth. Negative raised to the third is negative times another negative. It's going to make that positive 2x to the third. Negative raised to the second, it's going to be positive. Negative negative is a positive, and plus 8. For a change in signs, we start out positive, it's positive, 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 and positive. There are no changes, so the number of changes is 0, which means from Descartes here, rule of signs, the number of negative real zeros is either equal to the variations, there were no variations, or less an even integer. Well, we're not going to have less than 0. We're not going to have less than 0 real zeros. So our expectation here is there are no negative real zeros. Which means if we're looking for real zeros, all we have to do is look at positive numbers. Another theorem, I know there's lots of theorems. Like I said, this throughout time has been discussed probably ad nauseum. But rational zeros theorem, let f be a polynomial function of degree 1 or higher of the form. So we have our polynomial here. What this is saying is the leading coefficient can't be 0, and we have to have a constant. then if P over Q in lowest terms is a rational zero, P, so the top here, has to be a factor of this last one, and Q must be a factor of the leading coefficient. This is saying we can find, if there's a zero that can be written as a fraction, we can find it based off this last number and this first number. Well, how does that actually work? When we look at something like 2x to the third plus 4x plus 3, and we want to list potential rational zeros. Now, not all of these are going to be zeros, but if there is a rational zero, it's going to be able to be found in here. We look for the factors of P, which are the factors of this last number. Factors of 10, we could divide 10 by 1 or negative 1. And if we used either 1 or negative 1, the other factor would have to be plus or minus 10. So when we factor out 10, we could either use plus or minus 1 times either plus or minus 10. Some more factors, plus or minus 2 and plus or minus 5. Are there any other factors of 10? No, there are not. So we are done with those factors. Then factors of Q, factors of the leading coefficient, plus or minus 1, and 1 times 2, so plus or minus 2 are possible factors. There are no other factors for that leading term. Potential rational zeros are any fractions that we can make out of these numbers. And I already put the fraction bar there, but it's any possible fractions we can make out of these numbers. So if I start with the plus 1, we can do plus 1 over the plus 1, or I could use minus 1 over plus 1, or I could use, well, if I keep going here, if I use minus 1 over minus 1, we're going to get this right here. So really, as I'm doing this, so I don't end up with so many repeats, I'm not going to worry about plus or minus on the bottom. So the plus or minus on the top will take care of the possibilities. Then plus or minus 2, so I can do a positive 2 over 1, or I could do a negative 2 over 1. Plus or minus 5, I could do a positive 5 over 1, or I could do a negative 5 over 1. I can do a positive 10 over 1, or I can do a negative 10 over 1. When I simplify these fractions, we have so far 1, negative 1, 2, negative 2, 5, negative 5, 10, negative 10, and then those were all the fractions with 1 in the bottom. I could put 2 in the bottom. If I put 2 in the bottom with the plus or minus 1, we'd have positive 1 over 2 or negative 1 over 2. So 1/2 or negative 1/2. We could have positive 2 over 2 or negative 2 over 2. If we do positive 2 over 2, that's 1. We already listed it. Negative 2 over 2 is negative 1. We already listed it. We could do positive 5 over 2 or negative 5 over 2. We haven't listed those yet. We could do a positive 10 over 2, or we could do a negative 10 over 2. This one right here would be 5. We already listed it. This one's negative 5. We already listed that one. This list that I have down here, what that is are all the possible rational numbers that could be 0. So if we can find a 0 that can be written as a fraction for this function, again, if we can find a 0 that can be written as a fraction for this function, that 0 is going to have to come out of this list, is what this is saying. And that comes again from the rational zeros theorem. So if I want to know potential rational zeros or potential zeros that can be written as fractions, that's what rational means, is fraction, then it's going to have to come out of this list down here. Now something that might be helpful, just to kind of review something that you should have seen before, maybe you haven't, in which case I just wanted to show you this. This technique will be helpful with helping us find zeros as we get a little bit farther. It's called synthetic division. The way synthetic division works is it simplifies the division by looking at just coefficients. So here, if we took this polynomial up here and divided it by this polynomial, we can actually do that very simply with this thing called synthetic division. Synthetic division, the way it works is we take the number that would make this 0, so we take the number that makes this 0, which is 2, put it in there, and then we use only the coefficients from the top. So we'd use the coefficient of 1 for 1x to the third, negative 2 for the negative 2x squared, and 3 and negative 4, like that. Take the 1, drop it down, then take 2 times 1, put it there, 2 times 1 is 2, add. Negative 2 plus 2 is 0. Do the same thing, multiply, add, 2 times 0 is 0, add these, 3 plus 0 is 3. Multiply, 2 times 3 is 6, add, negative 4 plus 6 is 2. The way synthetic division works, after you drop the 1 down, then you multiply, add, multiply, add, multiply, add, multiply, add. That's how synthetic division works. And what this tells us is when we take this function, or this x squared, x cubed minus 2x squared plus 3x minus 4 divided by x minus 2, what we are going to get is, here these numbers tell us the coefficient, and this last number is the remainder. So what we are going to get is 1x. We started with x to the third, so this is going to drop it by a power, 1x squared plus 0x's plus 3 remainder 2. That's what synthetic division does for us. So what happens here is when we take this divided by this, we are trying to factor out an x minus 2. If we did that, the other factor would be 1x squared plus 0x plus 3 with a remainder of 2, or we can put the remainder plus 2. That's what this tells us. If we put a 2 here, 2 would make this 0. If that's a factor, the other factor would be 1x squared plus 0x plus 3. And then in this case, we have a remainder of plus 2. It didn't come out perfectly. That's how synthetic division works. With synthetic division, if you're missing a term, so if it's not 3, 2, 1, etc., you're missing that term, then when you do synthetic division, you just have to make sure you put a placeholder with a 0 in there. So notice here, these numbers here, they had the placeholder 0. Let's say this had been something like x to the third. I have no idea if this one would come out right. 3x plus 2. When you do synthetic division, if you wanted to divide this, or divide by, I don't know, x plus 1, again, I have no idea if this one's going to come out nice or not, but you would do negative 1, use coefficients, 1 for the x to the third, there's no x squared term, so you need to use a 0 as a placeholder, minus 3 plus 2, and then drop the 1. After you drop the 1, multiply, add, multiply, add, multiply, add. And if I just do that, so negative 1 times 1, negative 1, add negative 1, multiply 1, add negative 2, multiply 2, add 4. I got a remainder of 4, which tells me that basically the x plus 1 is not a factor of x cubed minus 3x plus 2. So, steps for trying to find these real zeros of a polynomial function. The first step would be to use the degree of the polynomial to determine the maximum number of real zeros. Then use Descartes' rule of signs. Then if it has integer coefficients, we can use rational zeros theorem. And then break it down, is what those last steps are saying. So let's try to do that once with an example. I'm going to skip this example. This next one, the process is the same, so I'm going to go to this example here. I'll do this example here. Step 1, use the degree of the polynomial to determine the maximum number of real zeros. Well, the degree is 4, so the maximum number of real zeros is going to be 4. The second step is use Descartes' rule of sign to determine possible number of positive zeros and negative zeros. So Descartes' rule of signs, when I look at this original one, we go from positive to negative, that's 1. Switches again, that's 2 changes. That's 3 changes. That's 4 changes. For Descartes' rule of signs, positive zeros, there were 4 changes up here. So the possible number of positive zeros is either going to be 4, or decrease it by an even integer, so down to 2, or again 0. Possible number of positive zeros is going to be either 4, 2, or 0. To find possible number of negative zeros, we have to do f of negative x, which is going, this should be f of x equals, is going to be equal to negative x to the 4th minus 2 times negative x to the 3rd plus 10 times negative x squared minus 18 times negative x plus 9, which negative to the 4th is going to be x to the 4th. We have negative to the 3rd, negative times another negative is going to be positive 2x to the 3rd. Negative squared is going to be positive. Negative times negative is going to be a positive, and plus 9. So we get same, 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 same. There are no changes. So for our negative zeros, we can expect there to be none of them. We don't have to look at negative numbers as possible zeros, is what that is saying. Don't look for negative numbers to be possible zeros. Step 3, use the rational zeros theorem. So the rational zeros theorem, step 3 here. Possible factors on the top of the fraction for possible zeros are factors of 9. Factors of 9 are plus or minus 1 or plus or minus 9, because 1 times 9, and then plus or minus 3, 3 times 3, so I think that are all the factors of 9. On the bottom, we could have possible factors of that coefficient, which is 1, which is only plus or minus 1, but again, if we use plus or minus 1 on the bottom as well, we're just going to have lots of repeats, so I'm just going to use just 1. Now, what this is telling us is that if there is a possible zero that can be written as a fraction, it's going to be in this list. What exactly is this list? If I start with the plus 1, we have plus 1 over 1 or minus 1 over 1. Plus 3 over 1 or minus 3 over 1, plus 9 over 1, or minus 9 over 1, which means possible ones are negative, or 1, negative 1, 3, negative 3, 9, and negative 9. That's my possible list based off of the rational zeros theorem. Then it says use substitution, synthetic division, or long division to test each potential rational zero. Well, I'm going to use a little bit of a combination of step 2 and step 3. In step 2, there were going to be no negative zeros. What that tells me is if there's no negative zeros, I don't even have to try these negative numbers. I can toss them out. So if there's a number that can be written as a fraction that is a zero, it has to be either 1, 3, or 9. I'm going to test 1 using synthetic division. So I put 1 in here using synthetic division. And my coefficients come from up here as 1, negative 2, 10, negative 18, and 9. Drop the 1, multiply, 1 times 1 is 1, add negative 2 plus 1 makes negative 1. 1 times negative 1 is negative 1, 10 plus negative 1 is 9. 1 times 9 is 9, negative 18 plus 9 is negative 9. 1 times negative 9, negative 9, 9 plus negative 9 is 0. I ended up with a 0. I ended up with a remainder of 0, which means that 1 is a 0. If I end up with a remainder of 0, it tells me that this number right here is a 0, which means if I put 1 into the function, I'm going to get 0. In order to put 1 into the function for the x value and get 0, a factor is going to be x minus 1. The leftover stuff comes from these coefficients right here. We started off with an x to the 4th problem, so now we're going to have a x minus 1. If that gets factored out, this big one is going to be x to the 3rd. So it's 1x to the 3rd minus 1x squared plus 9x minus 9 is equal to 0. So 1 is one of the real zeros. That's one of the factors. Then I'm going to keep going. So now I'm going to, I just depressed the equation. I'm going to go back to here. I'm going to go back a little bit to see if I can factor this down as well. Notice that this factor in this case has the same coefficients, 1 and negative 9, as this up here. So we had a 1 and we had a 9. Here we have a 1 and a 9. So what's going to happen again is that my possible rational zeros, because this 1 and this 9 ended up the same, those possible rational zeros are going to be the same as this list here, which means I can just try these numbers over again here. So when I try, I'm going to go ahead, try 1 with synthetic division to see if I can factor out another, if that's another 0. And this time I use these coefficients in here in this deep compressed equation. So I use 1, negative 1, 9, negative 9. I drop the 1. 1 times 1 is 1. Add 0. Multiply 1 times 0 is 0. 9 plus 0 is 9. 1 times 9 is 9. Add 0. Again, I got this right here. So this part here is going to factor into 1 made a 0. So it's x minus 1, the opposite of that. And the leftover stuff, we have 1x squared plus 0x's and plus 9. There's no remainder. And then this x minus 1 is still up front here. So far we've got this factored into x minus 1 times x minus 1 times x squared plus 9 is equal to 0. Well, could I keep going with this? Once I'm down to here, I'm down to the x squared problem. Then I can use those techniques from before. Can we solve x squared plus 9 equal to 0? If we can, that would mean x squared could equal negative 9. If we square root it, that means x could equal plus or minus square root of negative 9. That is not a real number. So that's an imaginary complex number. So it's not a real 0. Which means we just found our two real zeros right here, 1 and 1. The only real zeros are 1 and 1, which is 1. It would be our final grand total answer there. So all that work to find that there is only one real 0. Now to see, to get a little bit of a visual why that might be happening, if I go to a graphing calculator and I graph the equation over here. So if you look here, I've got the equation. Over here is the graph. This graph only touches the x-axis at one spot right there. So there's only, that's our only solution to this answer in this case. And what that is, those are techniques for trying to figure out what the zeros are. Good luck. And again, if this went too fast or you need a little bit more in-depth explanation, you can always go off to the left-hand side to where it has chapter contents, and then you'll be able to find the author's videos as well.